All right, we are on chapter 9.6. We're talking about pKa, something called pKa. And what's this all about? We talked about K, right, which is the equilibrium constant, whenever we were talking about weak acids. And we talked about P, meaning taking the negative log of a number. So the negative log of an equilibrium constant for an acid, we've talked about that subscript A, meaning acid. So basically the negative log for a weak acid's equilibrium constant, for example. That's all we're talking about. And so we're talking about the strength of these acids. Like, remember that table of weak acids where you could see the weaker and stronger weak acids? This is something that you're going to be able to decipher with pKa. So the acid strength is compared looking at the equilibrium constants. You know that. And so it's a relative number that explains dissociation and so forth. So the values that are going to be closer to 1, and you're going to see what I'm talking about soon, indicate that an acid is stronger. Even though it's a weak acid, could be a stronger weak acid, the closer to 1 it is. And the weakest weak acids are going to be farther away from 1, for example. So they're going to have maybe really large pKa's, for example, like maybe 14 instead of 2. That would be a weaker strong acid. You'll see that in a table coming up. So like we looked at the pH scale, right? And it's a whole lot easier and more simplified to look at whole numbers than some really large obscure number, right? Or by looking with scientific notation. So it's better to just use that log scale, like with pH. It's just it makes more sense. It's easier to talk about and understand to use a whole number. So we use pKa values to compare strength, and those values can range from 0 to 60. So you will always remember, you can write this rule when you get your test, that the smaller the pKa is going to be, the stronger the acid, right? So pKa small, acid strength bigger. Okay, you can think of it like that. Here's that table that I was talking about. So if you can remember water on this table, and that pKa for water is 14, that's really far from the value of 1, right? So this is the weakest weak acid, the weakest of the weak. In contrast to your hydrogen sulfate ion, which has a pKa of 2. So relatively speaking, that's a lot closer to 1, right? And you know, so that is on this table the strongest weak acid, right? All right, so just try and understand that concept. Spend a little time with it. This is a really short section. This is just kind of a comparison to show you the differences in reactions with acetic acid versus this ammonium ion. So if you're trying to determine, based on these reactions, where you have stronger or weaker acids, weak acids, you can look at the pKa, all right? And it will agree with kind of what you would already expect, maybe, where you have these charged functional groups. So you have a pKa of 4.76, where you have acetic acid, and a pKa of 9.20, where you have the ammonium ion. And so you know that then acetic acid, as you can see, is stronger than the ammonium ion, is a stronger acid, or it's just stronger than the ammonium ion. right, in general. Okay, so, all right. So let's go over some problems. Okay, where's my notability? Here. So you're going to have this table, but you're not going to have this arrow. You have to know this, okay? So let's work 9.49. Using this table, determine the stronger acid from the following pairs of acids. A. So let's look for H2PO4 minus dihydrogen phosphate ion. Okay, and we can see the pKa. All right, so we have 7.18 and HPO2 minus, right, 4. Here we go, our hydrogen phosphate ion, and we have 12. So 7.18 versus 12, and we are looking for the value that's closer to 1. That's the stronger acid when the pKa is closer to 1. So this is our answer, okay? B, H2SO4, H2SO4, or acetic acid. We know if you look at your strong acid table that we have a strong acid here. And we know that acetic acid is a weak acid. So you don't even have to look for this one. You just know which one is the stronger acid, and it's going to be this one. Okay, C, formic acid and carbonic acid. We have formic acid, 3.74, and carbonic acid, that's going to be 6.35. So formic acid. All right. Ammonium ion versus hydrocyanic acid. Right. So ammonium ion is going to be, where is that at? That is 9.20. And hydrocyanic acid, 9.21. So which one is going to be closer to 1? Your ammonium ion. So that's your answer. It's all of the first ones. Okay. 9.51. Which is a stronger acid, lactic acid, pKa 3.9, or pyruvic acid 2.5? Well, it's going to be the one that is closer to 1, which is the stronger weak acid. So that's pyruvic acid. All right. Closer to 1. pKa. Okay. All right, so now let's go back over 9.7. So here we're talking about the relationship between pH, all right? We're talking about ions here. pKa is talking about the strength, drug solubility, and diffusion. So we know that there's a relationship between pH and pKa. By comparing the pH and the pKa of weak acid solutions, we know if an acid is in its weak acid or its conjugate base form. We know if we've got something that's weak acid or conjugate base form. So we'll be able to tell, is the weak acid form present in higher amounts, or is the conjugate base form present in higher amounts in aqueous solution? So we talked about drugs before, and if molecules are charged, if you have a charged group on there, they're going to be soluble. So you want that. So companies will, add a charge there to make a drug more soluble in aqueous solution. You need that. But, if you're having this movement through the bloodstream, you have something soluble, you also have to get through hydrophobic barriers like the cell membrane, and you want to get into the cell. That's how the drug is active. So how are you going to do that? Well, so there's like this drug, propanol, a medication that people take for blood pressure. to lower their blood pressure and maintain less of a high blood pressure. The acidic form is charged, and the basic form is uncharged. Okay, so there's going to be different forms that you're going to have here, right? So it's going to depend all on pH and where that stands relative to pKa. Okay, so by comparing those two values, the pH and the pKa, for a weak acid solution, all right, we know if there's more of that weak acid or the conjugate base there, basically. Okay. So we're looking at propanol again. So the pKa is 9.42. That's the pKa. So if this drug were in the stomach where you have an acidic environment, it's going to be in its charged form, right? So there's different forms for that drug, and it's going to be in its charged form. Think about a chemical reaction with equilibrium. We're talking about like weak acids. So there are different forms, right? You go back and forth in the reaction with equilibrium. So in this case, in the stomach, the drug is going to be in its charged form at that pH. And so it's going to be soluble in the stomach. And then when you get to the small intestine, the pH is a lot different. It's going to get higher number-wise. It's going to become more basic. It gets to be about 8, remember? So, that's where we don't have as many of those hydronium ions. So the basic form is better for diffusing across the intestinal lining and getting into the bloodstream, which is what you want to happen. So that's actually ideal. And these shifts in these reactions follow Le Chatelier's principle, and you'll remember that. And look, we're talking about that here on the next slide. So if the pH is lower than the pKa, that pKa value, that means you have more hydronium ions. So that means that you have a more acidic form there. It's more acidic. All right, the lower the pH. Remember that pH scale. So more hydronium ions is more acidic. So that shifts the equilibrium to produce more of the acid form. And if the pH is higher than the pKa, it's opposite. That means there are less hydronium ions present. So think about that reaction. Look at the reaction and where you have hydronium ions and what's going to happen and how the equation is going to shift. So spend some time with that. The pKa and the Ka, so the Ka, it tells us the strength of the acid, how much it ionizes, dissociates in solution, and forms that conjugate base that's paired with that acid. Okay, so it tells you how much dissociates to form the conjugate base in the hydronium ion. And the pH tells us how much hydronium ion is present in the solution. So how much? Right, nothing has changed. That's still our definition for our pH, basically how acidic is it there. Okay, so the pKa values are constant at a given temperature, and that's what we're going with. So they don't change whether you add acid or base to the aqueous solution, but the pH changes if you add acid or base to a solution. So you notice this difference here, right? Make sure you understand what that difference is. So that pK is not going to change, but the pH is going to change. So knowing both helps you to determine whether the weak acid or the conjugate base is predominant in the solution. So many pharmaceuticals, many drugs have a weak acid or a base group, so that the weak acid form and the conjugate base forms are both there at equilibrium, because you need something that is both soluble and diffusible through the membrane so that the drug can be active. So oftentimes they'll make sure that these components are both present and can both be achieved in pharmaceuticals. So the amount of each form is going to depend on the pH levels that that drug's going to be in. So whenever designing a drug, you have to keep in mind, what sort of pH environments will that compound be passing through, and they can design the drug based with that information in mind. Okay. So I'm not sure, once again, why this equation is not coming up, but anyway, you should have pH equals the pKa plus the log of the conjugate base over the conjugate acid. So what is this equation? This is the Henderson-Hasselbalch equation. So it's kind of a big deal. So if we're talking about the relationships between pH and pKa, and we have one value and we're trying to get the other, this is the equation that we're going to look at. And what it does is it actually tells us the ratio of conjugate base to acid present. And this is sort of a modified version of that equation that we use here. So make sure you understand that one. All right. So that's for the equilibrium expression, Henderson-Hasselbalch equation. And you can use that also to determine the ratio of the acidic charged form of that drug, propanol, to the uncharged basic form in the stomach. So it turns out that that ratio is going to be very small, actually. And so you'll see that a majority of the propanol is going to be in the charged water-soluble form in the stomach. So we can also use the Henderson-Hasselbalch equation to determine what's happening with that drug in the liver. So that's going to be in the uncharged basic form, and that's going to be a form which can pass through cell membranes, right? So which is what you want to happen. That's the way that the drug can be active. Actually, you want the drug to get into the cells to be processed. So this is an equation that that you're going to be familiar with, that you're going to be able to recognize for sure. So in applicability, you have to think of the concepts of pH with drug delivery, right? So that's no surprise. Local anesthetics, those that are given sort of to just numb an area close to the site of injection, contain an amine functional group. So in its acid form has a positive charge, and its conjugate base form is uncharged. So the local anesthetic has to cross the nonpolar nerve cell membrane. The active form of the anesthetic is the charged acidic form, which can't cross the nerve cell membrane. So this uncharged form is what's going to get through the nerve cell membrane. The charged form is the one that relieves the pain. So you know that you have to have those forms all being there, all inclusive, because you can't just have every function that you need just one way or the other. So you have the charged and the uncharged forms for delivery and for function activity to actually relieve the nerve pain. Okay. So let's go over some problems. Let's see. Section 9.7. Okay, let's do 9.53. The anti-hypersensitive medication, alprazolam, is shown in an acid below. The pKa for the acid is 9.6. Which form is charged? Acid, conjugate base, or both? So we're told in A, so we're told that this is an acid. It's telling us that in the problem. And if we look, there is a charge there. So the answer here is this is an acid and it's charged. Okay, B. Which form, acid, conjugate base, or both, will predominate in a stomach with a pH between 1 and 3? See, it's acidic in the stomach, a pH between 1 and 3. So those are low numbers, right, on that scale. So let's say, like, for example, if we have a pH of 2 and a pKa of 9.6. If we have a pH lower than the pKa, the acid predominates. Okay, so if you think about it, in this case, then the acid predominates, right? Because you're given the pKa and they're giving you pHs, right? Which form, acid or conjugate base, will be able to more easily diffuse through a cell membrane? Well, you need the conjugate base, which is neutral. That's going to be neutral to diffuse through the cell membrane. All right. So let's see what else we have here. Okay, 9.55, an applied question. Consider the vitamin niacin, which has a pKa value of 4.85. So we're given the pKa. Underline what we have. A, will the acid or the conjugate base predominate at the following pH values? 3, 4.85, or 7.40? Let's set up a table. So we know that the vitamin pKa equals 4.85. So here we have pH 3. Here we have pH 4.85. And here we have pH 7.40. Okay. We'll make our little table to answer these. So we'll answer A, B, and C for each one. All right. Let's see. So let's talk about pH of 3 first for all of these. All right. So will the acid or conjugate base predominate at the following pH values? 3, 4.8, and 7.40. All right. Well, with pH of 3, you know that the pH then is lower than the pKa. So that means that we have something that is, it's lower, so we have something that's in the acid form. All right, so we have an acid. All right, and so what we're going to have in this case is the uncharged. So at this pH, is that form charged or uncharged? This is going to be uncharged, okay, in B. So in C, calculate the ratio of conjugate base to acid present at each pH. So what you have to do is you remember that Henderson-Hasselbalch equation. So you have pH equals the pKa plus the log of your conjugate base over your Oh, oops, over your acid. Okay, so what you're gonna have then, in this case, we have 4.85 equals pH is 3. So you'll end up with, you'll subtract 4.85 on each side, and you'll have 1.85 equals your log ratio. And what you'll have to do is 10 to the negative 1.85. You should get something like 0.014. Okay, so at pH 8.5, your pH is equal to your pKa. And so that means you have equal parts of conjugate base and acid. Equal parts. So you have a balance there. So then you have equal charged and uncharged. And if you divide one by the other and they're in the same amounts, that's going to be 1. Okay, and if you have a pH that is larger than the pKa, then that means you're going to have a predominant conjugate base. And that's going to be the charged form. Okay, that is the charged form. And we have, if you plug in everything, you should get something like 354 to 1. Okay. All right. So I think that's it for that one. No, there's another one. There's another one. 9.57. Procaine and lidocaine are used to numb the gums during dental procedures. Procaine has a pKa of 9.1, whereas lidocaine has a pKa of 7.9. Which do you think will relieve pain faster in the gums? Explain. So pause it and think for a minute. So both the pH and the pKa, all right, so pH is lower than the pKa for both. So since lidocaine's pKa is close to physiological pH, right? As you know, physiological pH, more conjugate base will cross the cell membrane. All right, and that's what we want the drug to do. So that's an effective drug. All right, so it would be lidocaine. Okay, let's go over our 9.8. So buffers in the blood. So you know it's important to maintain a certain pH in the blood. In a solution that's going to have both a weak acid and its conjugate base, or a weak base and its conjugate acid, is a buffer. And so a buffer is something that you have whenever the pK and the pH are the same, right? So you saw kind of what that looks like. So those things that are called buffers resist changes in pH, whether you add a little bit of acid or a little bit of base to that solution. Strong acids and bases are not parts of buffers, but you see the components here. And the point is to resist large changes in pH. So imagine how important a buffer is in the human body, because we can't have large changes in pH, and we do have stressors that can change pH. So we need buffers in our blood system. That is true. So what's happening is that those buffers are soaking up those ions and resisting those large changes in pH that way. So we'll talk about some examples. So we have, all right, this system called the bicarbonate buffer system. And that is how our blood is buffered, and we're going to maintain a certain pH in our blood. So we have dissolved carbon dioxide that is produced by cellular respiration, and it's going to travel through the bloodstream, all right, and be exhaled at the lungs. Although it's dissolved in the blood, carbon dioxide is going to have this equilibrium, all right, with water and form carbonic acid, and it's going to dissociate and form bicarbonate ions. So technically, carbon dioxide is not going to be an acid. It's not going to function as an acid. It doesn't have a proton. But you can see that protons are going to be coming from the water. So you have this buffered system here, and you can see this equation and how that works in equilibrium, how this exchange happens. All right. So we need to maintain physiological pH. That's really important for our homeostasis. We cannot have our pH going haywire in our body. When it does, we're very sick and we need emergency treatment. So the ability of an organism to regulate its pH, well, temperature, pH, solute concentrations, that's all homeostasis. It means you are at all of these optimal physiological parameters, right? You are at homeostasis, like you are at your happy levels. If you do not have the right temperature, like, you know, if your temperature varies from 98.6 to 100.5, like number wise, that doesn't sound like a huge difference, but you know, with temperatures that's wild, that's a high fever. Your body won't function right that way. Your cells and all of your proteins can only function under really specific physiological conditions. And those conditions, those conditions together, whenever they are good and well regulated, is referred to as homeostasis. So let's talk about some examples where homeostasis is affected by stressors, and how equilibrium needs to shift, or sometimes we need treatment to regain homeostasis. So a person might hypoventilate. And in this case, the carbon dioxide gas is going to build up in the bloodstream. But a buildup of carbon dioxide in the bloodstream is going to shift the reaction, right? So you have this one stressor, the equation is going to want to shift the other way. So then you end up having a buildup of hydronium ions in the bicarbonate equilibrium response and reaction, and that chemical reaction in the blood then is going to be more acidic because you have more hydronium ions, and that's called respiratory acidosis. Your blood pH is going to be too low, so you have to treat this with a base, right? So intravenous bicarbonate. So you'll have an IV of a bicarbonate, like sodium bicarbonate sometimes, something like that. So you'll notice that all of these things can be represented by these equilibrium equations. And Le Chatelier's principle still applies. When one thing goes up, the reaction shifts the other way, and you have to know what to do to correct for that situation. So when a person hyperventilates, you start breathing too fast, maybe you're panicking, something like that, you'll have too much CO2 from the lungs. And in that case, you're drawing hydronium ions from the bloodstream, out of the bloodstream, and you're going to have a more alkaline blood at the time, and that'll be basic. So alkalosis, basic. Respiratory alkalosis is what you'll hear that called. And it can be reversed by, if you've ever seen somebody breathing fast, panicking, you put a paper bag over their mouth, like one of those brown bags. And, you know, you've probably seen that on TV or something before. And that will keep some of that CO2 that was exhaled from the lungs instead trapped and available right there, ready for that next breath, so that it can shift the equilibrium equation, so that the blood is not so alkaline anymore, return some of that CO2 and sort of reverse what's happening. Okay, so you'll have a question that refers to that in just a second. And so here's a table, right, that shows you some descriptions and symptoms of what happens if somebody is having an episode of respiratory acidosis or respiratory alkalosis, or metabolic acidosis and metabolic alkalosis. Metabolic acidosis is something that happens a lot of times in people with diabetes, for example, and or even with renal disease, hepatitis and cirrhosis. It's something that can be treated, like I said, with sodium bicarbonate. So you're treating that acidosis with a base, for example. And if you look here, like respiratory alkalosis, where you'll treat this sort of thing that's going to happen, where you have this high breathing rate, and you're losing too much carbon dioxide. You'll have to try to eliminate whatever has caused that anxiety, if that's the cause of the problem, and you can put a paper bag over that person's mouth to breathe into, to sort of reverse what's happening. And we're going to have chemical reactions in our body happening all the time that are going to be stressors that change the pH of the blood depending on how many hydronium ions are there. You can have too much or too little, but you don't want too much or too little. So diabetics in their metabolism use fatty acids as a carbon source. And they do this because they don't respond to sugar, right? So one of the byproducts of that chemical breakdown of fatty acids is going to end up causing acidosis. So you can see here in this equation that what you can do to balance out this reaction where you have metabolic acidosis is give bicarbonate. Give some of that bicarbonate so that the blood then is less acidic. So that makes total sense. And in opposition, when you have the blood is too alkaline, that's metabolic alkalosis. So here is not enough hydronium ions, right? Too little H3O plus. That can happen if somebody's been throwing up too much for different reasons. In that case, the pH is going to maybe be higher than 7.6, and by a good bit possibly. So to lower the pH, they'll give ammonium chloride. Therefore, you know that carbon dioxide and bicarbonate are going to be tightly regulated in the body. So we saw that the bicarbonate buffer equilibrium is going to shift based on how much CO2 or bicarbonate is present in the bloodstream. And if somebody is having an asthma attack, for example, they're not going to be exhaling enough CO2. So the CO2 is going to increase in their body, and they're going to end up having an acidic blood level, respiratory acidosis. So the body is going to then try and shift to change the concentration of bicarbonate then. So that's a secondary response to restore the balance in pH, and that's called compensation. So understand what compensation is, right? So in that person, CO2 is going up with the asthma attack, all right? So you have like this person. It helps to draw things out sometimes. All right, they're breathing too much, or rather, it depends. They're not able to breathe enough. Okay, so you're going to have or they're not exhaling properly. You're going to have CO2 increasing in the blood. right? Oh, sorry, I said that a little silly, but you can see here, unable to expel enough CO2. So that person has increasing levels of CO2, and then the body is going to try to respond by changing the concentration of bicarbonate. So the reaction is going to try to do the opposite, right? So you're having a change, for example, in the reactants, and think about what the reaction wants to do. So the body compensates for the change in CO2 by keeping more bicarbonate in the bloodstream. And one of the ways that this can happen is for the kidneys, all right, your filters there. I know my kidneys and my lungs kind of look alike, right? So your kidneys, all right, are going to try to decrease the bicarbonate excreted in the urine to offset the higher CO2 levels and maintain equilibrium. All about maintaining equilibrium. Okay. So that's my silly drawing of kidneys. The kidneys want to keep bicarbonate. So it helps to kind of write things out whenever you're trying to remember them. So the body can also try and control the carbon dioxide that's there by changing the ventilation or breathing rate. So that's kind of like an automatic thing. And it has to do with chemical signals in your brain that are going to let you know, hey, I have too much or too little CO2. Those sensors that are going to be picking up those sorts of stressors in your respiratory center in the brain control the rate of and the depth of the breathing, how big of a breath you take, how often do you breathe. And if the CO2 levels increase, right, the sensors compensate by saying, hey, we have a lot of CO2, it's increasing, and the autonomous nervous system increases the rate of breathing then to lower the CO2 levels, okay? So you have this reaction that happens right here. You can see if the CO2 levels rise, the lungs have this compensation response, increase the ventilation rate. And if CO2 drops, lungs compensate by decreasing the ventilation rate. All right. So if you have the opposite response, all right, where you have too much HCO3 and those levels rise, kidneys compensate by increasing the urine output, and contrary-wise, they can compensate by decreasing the urine output. So there's this axis that will maintain this equilibrium between the lungs and the kidneys here in your bicarbonate system. Okay. So I think that's it. And that's it for chapter 9. Let's go and work some of those problems for 9.8. So 9.59, I think that's it. Yep, this is the only one. So during a stress or trauma, a person might start to hyperventilate, right? They're breathing too fast. You're going to give them a paper bag in order to avoid fainting, right? So see the chemical reaction here. How does the blood pH change during hyperventilation? So A, what's happening is you are lowering the CO2 levels here, the carbon dioxide in the blood. Let's be specific. So then that means, so you're decreasing hydronium ions. So the blood pH is becoming more acidic, right? I mean, the blood pH is increasing. No, don't listen to what I said out loud. The blood pH is increasing. If the pH is increasing, that is more basic. That is more basic, right? So, because I said this wrong. the hydronium ions are decreasing. Oh, that's where I started to confuse myself. So the hydronium ions are decreasing, all right? If you would have more hydronium ions, that would be acidic. They're decreasing. The blood pH is then rising, and you have a more basic pH. So let's do B. So in which direction will the bicarbonate equilibrium shift? So if we are decreasing carbon dioxide, all right, remember your reactants in your products. If we're decreasing our reactant, then the reaction is going to want to increase the reactants. So we're going to want to, the equation is going to want to shift left. The reaction is going to want to shift left. Okay. So C. What is this condition called? This is respiratory alkalosis. So just kind of have some note cards for those, and there's already a table for those different pathologies that you can have, those different conditions. So D, how does breathing into a paper bag help to return pH to normal? So D. So it helps us to more easily inhale CO2, right? Because that's what you exhaled. So you'll just inhale the CO2 again. So increasing the reactant, right? Like what the reaction wants to do to maintain equilibrium, right? So the reaction, because the reaction will want, if we though this time are increasing the reactants, the reaction will want to decrease reactants. So the reaction itself this time then is going to want to shift right away from the reactants. All right. And so ultimately, we are going to lower the blood pH, because what we are doing is going to give us less hydronium ions and lower the blood pH. More hydronium ions. The reaction, I'm so sorry. The reaction is going to want to give us then, so more hydronium ions, lower the pH, and so we're going to then be more acidic, which is better to shift away from a situation that is too alkaline, respiratory alkalosis, right? So how does breathing into the paper bag help to return the blood pH to normal? So we're easily going to take in more of that CO2. So we're affecting the reaction this way, and the reaction is going to want to shift in this direction because we have added more reactants. Reaction is going to want to make more products then with Le Chatelier's principle. So we have more hydronium ions. That's going to go up. So the pH is going to go down, which is more acidic. Okay. All right. There you go. Which direction will the equilibrium shift as the pH returns to normal? Well, we've already talked about that pretty much in our discussion. So, all right. Okay, good. All right, that's it for today. Have a good one.